How humans built their first space rocket.
Okay, let's jump right into this. Have you ever been watching a launch, or maybe just spotted a satellite tracking across the night sky, and stopped to wonder how we actually managed to leave Earth in the first place? I mean, escaping gravity? It definitely wasn't magic, and it for sure wasn't some overnight accident. It was the result of a handful of incredibly persistent, brilliant minds solving these massive, seemingly impossible physical barriers through just sheer math and engineering. So today, this explainer is going to serve as your ultimate study guide to those pioneers. We're going to break down exactly who built the foundation of modern space travel and zero in on the specific innovations they brought to the table.
Here's a quick look at our syllabus for today's explainer. We're going to cover the origins of rocketry, Tsiolkovsky's space theories, Goddard's work as the liquid fuel pioneer, von Braun and the V2, and we'll wrap up with the dawn of the space age. All right, Chapter 1, The Origins of Rocketry and the Accidental Inventors.
So to really understand this, we have to rewind nearly 1,000 years, long before anyone even knew what a vacuum or an orbit was. We're talking 13th century China, where a completely different intention led to a massive global breakthrough. Inventors there discovered gunpowder, that classic mixture of charcoal, sulfur, and saltpeter. At first, it was just used for celebrations, fireworks basically. But eventually this really critical realization happened. If you pack that explosive mixture inside a closed tube, the expanding gases from the explosion only have one way out, and that escape route propels the entire object forward. So yeah, space travel tech essentially started as a fireworks display gone wrong. It was a happy accident that turned celebrations into fire arrows for battle. It was simple, and honestly totally inaccurate, but it was the very first fundamental realization of rocket propulsion.
Moving on to Chapter 2, Tsiolkovsky and solving the vacuum problem.
Let's fast forward to the late 19th century. There was this Russian schoolteacher named Konstantin Tsiolkovsky, and he decided to tackle what everyone thought was a deal-breaker: the vacuum of space. Back then, people logically thought, well, if there's no air up there, what exactly is the rocket pushing against to move? Makes sense, right? But Tsiolkovsky, he applied Newton's third law of motion to rocketry. He mathematically proved that a rocket doesn't need air to push against. It moves because it pushes its own mass, specifically its exhaust gases, backward. That action creates an equal and opposite reaction, violently thrusting the rocket forward. This was a huge aha moment in history, proving that rockets could absolutely work in the vacuum of space.
And he didn't stop there. He also came up with the whole concept of the multi-stage rocket. Tsiolkovsky realized that carrying heavy, empty metal tanks all the way up to orbit was just terrible for efficiency. I mean, it's literal dead weight. So he theorized this step-by-step process. You burn fuel for the initial heavy launch, you physically discard the empty tanks to instantly drop your mass, and then you ignite the next stage to keep going. Every single modern launch vehicle we see today, from the Apollo missions right up to today's commercial flights, still relies entirely on this exact weight-saving technique.
Which brings us to Chapter 3, Goddard, the liquid fuel pioneer, and solving the efficiency problem.
Enter the American physicist Robert H. Goddard. He's the guy who finally took all this math off the chalkboard and tackled the massive issue of propulsion efficiency. Up until Goddard, inventors were basically still just playing around with advanced gunpowder and solid explosives. But Goddard had this fierce, radical belief that if we were ever going to reach the insane speeds required for space travel, gunpowder just wasn't going to cut it. It was way too weak. He hypothesized and then set out to prove that liquid fuels would be significantly more powerful, controllable, and efficient. After years of these really painstaking, grueling experiments in a field in Massachusetts, on March 16, 1926, Goddard successfully launched the world's very first liquid fuel rocket. It flew for 2.5 seconds, and it went 12 meters. Seriously, 12 meters. By today's standards, that seems completely insignificant, right? But scientifically, it was an absolute game changer. This tiny little machine definitively proved that liquid fuel propulsion actually worked in the real world. But as with a lot of great innovators, people just didn't get it at first. The public actually mocked his tiny little 12-meter flight. The New York Times even wrote this scathing editorial claiming Goddard lacked the knowledge they teach daily in high schools, literally questioning his grasp of basic physics. They were completely oblivious to the fact that his liquid fuel principles were exactly what would eventually take humans to the moon. In fact, kind of a funny side note, 43 years later, right as Apollo 11 launched, the Times actually issued a retraction. It's just a great reminder that true innovation often looks foolish to the status quo, right up until it completely changes the world.
All right, Chapter 4, Von Braun, the V2, and engineering the edge of space.
As we enter the World War II era, we transition away from solitary guys doing experiments in open fields to heavy, state-sponsored engineering largely led by Wernher von Braun. Now, the creation of the V-2 rocket is a really complex, dark chapter in history. It was built as a devastating weapon of war, and it caused immense destruction and loss of life. But strictly from a historical and technological standpoint, it represented a massive engineering leap forward. The V-2 actually became the first human-made object to reach the edge of space, climbing more than 100 kilometers above the Earth. It proved, once and for all, that large-scale, liquid-fueled guided rockets could actually break the boundary of our atmosphere.
And finally, Chapter 5, the dawn of the space age and the race to the stars.
After the conflict ended, both the United States and the Soviet Union captured this V-2 technology, and that kicked off a timeline of just incredibly compressed innovation. I mean, just think about the sheer speed of this era for a second. In 1926, Goddard is launching a rocket a measly 12 meters into the air. By the 1940s, the V-2 is breaking the 100-kilometer barrier. Then, bam, in 1957, the Soviet Union launches Sputnik 1 into orbit. And just 4 short years after that, in 1961, Yuri Gagarin becomes the first human being to travel into space. In the span of just 35 years, we literally went from struggling to get a little metal tube off a farm field to putting a human being among the stars.
It really represents this profound global shift. The same technologies that started out as fire arrows to scare enemies in the 13th century and evolved into terrifying weapons in the 20th century were finally being transformed. They were finally fulfilling that ancient, peaceful dream of leaving Earth's atmosphere for the sake of scientific discovery. Because of this, we were able to launch satellites. We could study our own planet from above. And ultimately, we took that miraculous first step onto another world.
So if you're building a mental cheat sheet for this study guide, here is exactly how that foundation was laid. The ancient Chinese gave us the absolute basics of propulsion. Then Tsiolkovsky came along and provided the vacuum flight theory and the concept of staging. Goddard followed up by delivering the high-efficiency liquid fuel engine. And finally, von Braun's team provided the heavy industrial engineering required to push us all the way to the edge of space. Looking at it like this, you can clearly see how every single breakthrough was an absolute prerequisite for the next one. Nobody got to space alone, right? They were continually standing on the shoulders of the innovators who came just before them.
And that brings us to today. Every single modern satellite that runs your GPS, every rover snapping photos of ancient riverbeds on Mars, and every one of those crazy new commercial rockets that return to land themselves on a drone ship in the ocean, they all exist because of the pioneers we just covered in this explainer. The foundation has been laid, but honestly, the journey to the stars has really only just begun. So it leaves us with one incredibly exciting question. Armed with this foundation, who from the generation watching today is going to step up and write the next great chapter in space exploration?